Okay. Hopefully we're on the right track now. So what do we got here? Oh yeah, this is the best part. Resonant circuits. Uh, I don't think in the previous one we talked much about impedance and reactance. I'm not sure why, but you get a lot of that in the general and extra. Uh, a resonant or a tuned circuit, sometimes they call them tank circuits, is composed of an inductor and a capacitor. I mean, you could have multiple ones, but the effect is the same as a single inductor and capacitor. They can be connected in series or parallel. They will resonate at the same frequency. It doesn't matter whether they're series or parallel. The difference is their behavior. And if it's a series resonant circuit, in other words, figure A, here, you've got an inductor in series with a capacitor in this circuit, and there may be some series resistance. In the real world, there'll be resistance in this inductor and some in the capacitor. In the case of the parallel circuit, okay, you can have the same value inductor and capacitor, but they're in parallel. And what happens is in the series circuit, when it's at the resonant frequency, it's going to have essentially zero impedance. So the circuit will only see, if it was resonant, what you would see at that frequency is just the resistance of R. The L and the C are going to cancel out. And that's because they are reactive components and are frequency sensitive. Oh, goodness. So in the case of an inductor, it has a reactance of 2 pi times the frequency times the inductance. And that will be in ohms. So it's like resistance, except it's opposing AC current, not DC current. In the case of the capacitor, it's going to be the reciprocal of or 1 over 2 pi f times the capacitance. That will also be in ohms. And that will, we represent that as a negative because we get into complex numbers and it will be on the complex plane as a negative or a minus j, which is the square root of -1, where the inductive reactance is going to be positive. So in the case of a resonant circuit,
it's 11 hours.
Say that again.
Sorry, that was just my clock telling me it was 11.
Oh, okay.
Sorry about that.
In the case of a resonant circuit, it's resonant when the reactances are equal and opposite, and they cancel each other out. So if I had those two values for L and C, or whatever frequency, let's say they were both 1,000 ohms of reactance. One is plus and one is minus. They're going to cancel out. So all I'm going to have in the circuit is the resistance R. In the case of the parallel circuit, L and C cancel out, but because they're parallel, we take those as reciprocal values, go through 1 over this sum of the reciprocals, and you come out with a very high impedance. And that's the difference between a series and a parallel. In the series circuit at resonance, it appears to be a short circuit or 0 ohms. In the parallel circuit, it's going to look like an open circuit or infinite ohms. So in the parallel, you'd only see the value of R at resonance. When you get slightly off resonance, then you get the combination of R plus whatever the effective impedance is of the LC network at that frequency. And I know that sounds kind of complicated, but it's actually not as complicated as you think. What's actually happening in a resonance circuit, as you remember, we defined inductance as the ability to store energy in a magnetic field. And we define capacitance as the ability to store energy in an electric field. So what's happening in a resonance circuit is, let's say we start with a charge on this capacitor, so it has a certain amount of energy. And if there's no current flowing anymore, if it's charged up, it's going to start discharging and causing a current to flow in the opposite direction into this inductor, which initially is going to try to resist it. But that energy is going to create a current through this inductor, which is creating a magnetic field, okay, as we just talked about from Lenz's law, and storing that equivalent energy. When it gets to maximum storage, the magnetic field starts to collapse because there's no more current or there's no change, and it goes back into the capacitor. So that energy just moves from being stored in the inductor, that's a magnetic field, to the capacitor in the electric field. So it's the same amount of energy going back and forth at whatever the resonant frequency is. Did I make that clear or muddy the water? Okay, here's a plot of a series inductor capacitor resistor. And as you see down here at, what is this? 40 kilohertz, it's several thousand ohms. And as we approach the resonant frequency, it goes down to, in this case, 1 ohm, because there's a 1 ohm resistor in series with it. And then as we go higher in frequency, the reactances are no longer equal. So we have the resistance plus whatever that effective impedance is, and it goes back up into several thousand ohms. In the case of the parallel circuit, we start off at 0 because the inductor at a very low frequency has essentially no impedance or reactance, so it looks like a short circuit, like a DC. As the frequency increases, then you start to see an increase in the reactance. And when it gets up to the resonant frequency, it's also equal to the reactance of the capacitor, which is now starting to go down in impedance. So they're both equal at this point, where we're up, in this case, 50 ohms as opposed to 0, because we had a limiting parallel resistor there. So you can see in the series, it starts off high, goes to essentially 0 at resonance. The parallel starts off at essentially 0 and goes very high at resonance. So which of the following is a resonant or tuned circuit?
A.
Good. Voltage regulators have nothing to do with it. I don't understand how a resistor circuit could be used to reduce the standing wave ratio. It could reduce the amount of the wave, but not the ratio. And a hi-fi circuit has nothing to do with it. Which of the following is combined with an inductor to make a resonant circuit?
D, capacitor.
All right. Has to have reactive components that are opposite reactances. In other words, capacitor and an inductor. Okay. Talk about switches again. Now we're going to talk about a single pole double throw switch, where it can switch one circuit over here, the battery, between two other circuits, either this lamp or the LED. So what is the function of a single pole double throw switch?
C.
How many Charlies we got? So a single circuit is just a single pole, single throw switch. And a double pole, double throw could open and close two different circuits. Another component is a relay. A relay is an electrically controlled mechanical switch. So we have a solenoid, which is like half a transformer. So when we run current through it, it's going to create a magnetic field. And that magnetic field is used to attract this switch lever. So it's normally got a constructed with some sort of spring to hold it in one position. And then when the magnetic field is created, it pulls it towards the magnet or the solenoid and changes position of the switch. So it's a way to remotely control a single pole or double throw switch. So what is a relay?
An electrically controlled switch. A.
Okay. Meters. They're used to display a quantity as some numerical value, either a digital type display or an analog, where it has some scale and a needle pointing to a numeric value. You're seeing less and less analog displays nowadays. Most everything is going digital, or even a display like a TV where you can do graphics and represent analog or digital meters or any other kind of thing you want. Normally, you're going to have these representing the output of a power supply. Usually you'll have a voltmeter and a current meter on the front. If you've got a power amplifier, it will normally have some meters like plate voltage, grid current, or drain current in case of a transistor power amplifier. May also have a power output meter on it. So they're used in a lot of things. You'll probably wind up if you get an HF set up, having a power meter, an SWR meter, things like that, in addition to your radio and stuff. Here's some examples of, in this case, they're all analog type. You've probably seen view meters on old audio equipment. In the case of receivers, they'll usually have some sort of S-unit display. A lot of times it's digital now, but you'll have S 0 through 9, and then 9 plus whatever this is. This is just a straight voltmeter display. So which of the following displays an electrical quantity as a numeric value?
Meter.
All right. Integrated circuits. So that's just a lot of semiconductors, resistors, capacitors, maybe even some other analog type things on a single substrate, usually silicon. So because silicon by itself is an insulator, you can what they call dope certain areas and create transistors and add resistors and things like that all on the silicon substrate. Kind of like a printed circuit board, except it's a crystal slice, and they do stuff very, very, very small. Your normal microprocessor, they're up into the probably tens of millions of transistors on that little die, which is maybe less than an inch square. You can have analog functions on some of the integrated circuits. Typically, these will be things like linear voltage regulators. In some cases, could be a switching regulator, where it's analog value. So what is the name of a device that combines several semiconductors and other components into a single package?
Integrated circuit.
What we do is integrate stuff on the same piece of silicon. What type of circuit controls the amount of voltage from a power supply?
Regulate.
All right. Another component, a fuse. It's used to break a connection to protect devices downstream of the fuse from an overload. It may or may not be successful, but it's better than letting it start a fire. So if you didn't have a fuse and you had some short or whatever, you're going to get a high current, and it's going to create enough heat that eventually something is going to catch on fire or blow up. What electrical component is used to protect other circuit components from current overloads?
Fuse.
Let's see, and we hadn't talked about varactors. That's a voltage controlled capacitor. It's actually a kind of a special case diode. Shielded cables. You use shielding on the cable, and it creates what we call a Faraday cage, where it will essentially block signals from coming through and interacting with the conductors inside the shield. And usually you connect that shield to ground, but it's based on the different potential between the shield and the conductors inside in that electric field, and it blocks outside fields. If it's totally enclosed. Now, in this case, it's obviously open on the end, so there would be some energy that gets in there from the outside. Every place you would have a break. Which of the following is a reason to use shielded wire?
See.
To prevent unwanted signals from coupling or affecting it. So we learned resonance circuits. A series has a very low impedance at resonance. Parallel is very high. A single pole double throw switch will switch a circuit between two other circuits. Relays, electrically controlled mechanical switch. Meters display numeric values of a quantity. Integrated circuits are multiple devices in a single package. A regulator or voltage regulator maintains a constant voltage from a higher voltage source. The fuse protects other components, and shielded cable prevents coupling of unwanted signals.